But first to kick off is Christian Schaffner, talk about the quantum random oracle model. And Christian is a honorable member, I might say, of QuSoft. He is very well known and co-inventor of the bounded storage, quantum bounded storage model. And I'm not sure you will talk about that, but this is something he co-invented, and he has been in Amsterdam for a long time. I forgot exactly for how long, but
12 years.
He's 12 years, so he's almost Dutch. And his Dutch is also very good. And he also won a VD grant, and he is well, one of the members of QuSoft. And I give you the floor, Chris. And I'm very happy that you can give a talk.
Thank you very much. All right, I'm really happy. Can you hear me? This microphone is on. Great. To kick off this series with a maybe rather technical talk about quantum cryptography. And I'm also would like to apologize that I did not send any abstract, so you're in the dark here. But so was I until 2 days ago. So this talk was only really finished like last night. So I could now write an abstract, or maybe you can after the talk, but sorry for that. I'm going to talk about the quantum random oracle model. So here is actually a picture of the Oracle of Delphi, where the ancient Greeks used to go to and get their questions answered, often in a very cryptic way. So it was not always clear that they actually had more information when they left than what they had when they came. And this is going to be my picture for the random oracle model. So in the first part, I'm going to talk about the importance of it, or what it is in classical cryptography. And then we're going to switch gears and look at what happens if we throw quantum into the game. And then I would like to explain you a recent tool, and when I say recent, it's really like last year, I came up to analyze this kind of settings. And at the end, if I have time, I will talk about some of our results in that model. All right, so that's the plan. Let's start off with a little quiz. First of all, a random oracle is basically a random function. And in this talk, often these functions just map n-bit strings to n-bit strings. And my question to you is, how many such functions are there, actually? So it's a combinatorial question that I like to ask in my crypto course, and maybe some of you also like that to ask to your students. But I'm curious if you know the answer. So I'm sure some of you have actually followed this link that was up there for a while. So this is the same question again. Now I see it on my screen, but you not on there. So here, how many functions are there mapping n-bit inputs to n-bit outputs? So maybe just a quick show of hands. Who thinks that are n factorial? 0. Who thinks that there are 2 to the n of these functions? Say one hand. Who thinks it's 2 to the 2? Who thinks it's 2 to the n factorial? Another one hand. Who thinks that it's huge? It's like 2 to the 2n? I see maybe a third of the people. And who thinks it's even larger? It's 2 to the n times 2 to the n. And that's maybe half of the room. So let's see, I don't know, there's some statistics here, I hope. Some people filled it in. Oh yeah, so if you use the joker, so this is actually the correct answer, the last one. And let me explain you why. So you can basically write down a truth table of such a function. So that's just like writing down a big table. Basically you have something like 2 to the n rows. So for every possible input string, so you start with a 0 string, then 0, 0, 1, etc. So you have 1 row per input. You write down what the output of this function would be. So you have n columns. And every entry of this 2 to the n times n sized matrix has either 0 or 1 in it. And as soon as you change 1 bit, well, then you've changed the function. Also, you have for every entry you have a choice of 2 options, either 0 or 1. So you actually get 2 to the size of the table, which is n times 2 to the n. And let me tell you that this is a huge number. For already n equals 6, you get something like 2 to the 384. Which is larger than the number of atoms in the universe. So the number of functions mapping as 6-bit strings to 6-bit strings is already larger, and it's insanely large. And in fact, you need something exponentially in n many bits just to specify that function. So these are the number of possible functions, but just to specify such a random function, you need exponentially amount of bits. And that usually doesn't go well with what we call efficient players. And usually efficient players, they run in polynomial time in n, and so you cannot even give, they don't even have the time to read the description of such a random oracle. So it's a huge thing. Another thing we have to talk about are hash functions. So what are those? Hash functions, a cryptographic hash function takes arbitrary length input strings, so that's this star here, that could be an empty string, or it can be a 1-bit string, or be a 100-bit string, so some finite size length string, and it maps it to a fixed output size n. So think of it as you have a huge message, and you want to kind of hash it down to something small. Often this n, the number of output bits, is something like 256. So in fact, for this particular hash function that you can look up on Wikipedia, these SHA-3 functions, you get something like that. So this is also copied from Wikipedia. So you have, if you apply this to this sentence, the quick brown fox jumps over the lazy dog, encoded in ASCII, so this binary string, if you hash this string down, you get these 256 bits specified in hexadecimal. And if you change just a single bit, basically, of this message, then you will get a completely different string. And so it will hash to something totally different. And that's exactly what we want, because an ideal hash function, in fact, should behave as a random oracle. And remember, a random oracle is just if you have two different inputs, you get totally independent outputs. And that's basically where the random oracle model comes in. Let me illustrate maybe further a property of this. Namely, this is what we call collision resistance. So one can prove this theorem, and it's not very hard. So for a random function, so for a random oracle f, it's difficult to find two colliding inputs. So what do we mean by that? Well, formally, for any adversary who makes q queries to f, so that's this here, so a queries f, and he produces two outputs, x and y, the probability that those are different and they evaluate to the same function output is pretty small. It's O of q squared over 2 to the n. So if q is a polynomial, then this is exponentially small in n. Here's a simple proof. Let x1 to xq be the list of the adversary's queries to f. So, and we can, without loss of generality, assume that he makes different queries, and there's no need for asking the same thing twice. Then, if you just have such q different inputs and we evaluate a random f, then what I just said, you get independent random outputs, and the probability that two of them collide, you can upper bound it by this term. Intuitively, there's roughly like q choose two pairs, so that can upper bound by q squared, and the chance that two of them collide is something 2 to the n. So that's kind of a property we get from a random oracle. And now let me tell you what the classical random oracle model is. So what we call in crypto the random oracle model is basically a heuristic to analyze hash functions that are used in cryptographic proofs. So what do I mean? Let's say we have some protocol that uses a hash function as a subroutine. And we're going to see some in a second. And we have an adversary who kind of interacts with this protocol, maybe plays a role in this protocol, or some challenge response game. And this guy, in the real world, he knows H. And so you can look up SHA-3 on Wikipedia. And what we now do in this heuristic, in the formal random oracle model, we do the following. We kind of replace every call to H with a query to the random oracle. So we kind of externalize this function. So we now have a random oracle over here. So that's a real random oracle. And we kind of allow, well, we kind of take away this knowledge from the adversary that he knows H and he can run it himself. And we make him interact with this random oracle. So he can still kind of query values to this random oracle. However, we will observe what he does. So that's kind of what I mean. So adversarial queries are observed. So you as a one who's like watching the protocol, or in most often actually in cryptography, the reduction around something, you can observe what kind of queries he does, so what he queries to the random oracle and what he gets back as an answer. And so that's kind of convenient, because we don't have to give the description, which we just saw is insanely big, to that guy. We just basically tell him whatever he wants to know. So that's, in that sense, it's convenient. And so, for instance, that means that an adversary who has not asked a particular input yet, he has no idea what the output h of x will be. It will be an independent and uniform value. So And that's kind of the abstraction we do. However, there's also criticism about this model, because there exist some weird examples, in particular signature scheme, and I'm going to explain in a second what that is, and that is actually secure in this random oracle model. Under this heuristic one can prove security. However, when you do what you actually want to do, namely replace this oracle with an actual hash function, then the scheme becomes insecure. So that's pretty strange. However, people don't care too much about it because they are still very artificial examples. So somehow this heuristic has been used many times, and somehow it seems to deliver. So no realistic example of this weird thing are actually known. So the common view is kind of, well, it's much better to at least have a proof in a random oracle model than having no proof at all. So it's fine to work in that model. Now, what can you do with it? Well, let me explain you what digital signatures are. So a digital signature scheme allows you to kind of digitally sign a message. No? Let's say Alice has a big message she wants to transfer to Bob, and it's over an insecure channel, so Eve has some control over that channel. And a signature scheme is basically a so-called public key crypto system, where first of all it has a key generation algorithm that Alice can run, and it will give her a pair of keys. So they always come in pair. It has a public part and a secret part. And the secret key she keeps for herself, and the public key she can publicize. So also the eavesdropper, Bob, anybody can look up her public key and know her public key. And the secret key signature scheme then allows the secret key holder to sign this message. So there's kind of a procedure to put a signature on this electronic message. And then once it's sent over the channel, everybody can go, everybody who has the public key can verify that this is a valid signature. And if indeed this verification checks out, then you know the message has not been tampered with, and in fact it has been signed by the person who holds the secret key. So that's kind of what we want from a digital signature scheme. And that's great, and it's actually used all over the place. So here's a slide from Bart Prenell from a talk he gave at QCrypt 2014, so that's already 5 years old, but it just shows huge numbers. For instance, he counts the number of devices of PCs, mobile phones, tablets, something like bigger than 3 billion devices that all need to be updated, hopefully. You know, the security holes need to be fixed, and so you need to update your firmware or your operating system. And how do you do that? Well, you get a software update from somewhere, but how do you know that this is the genuine one? So these software updates are digitally signed, so that hopefully only the actual software provider can provide you an update. Otherwise, of course, you can infect any computer like that. So this is maybe the very important and a huge use of digital signature schemes. Other examples are smart cards, like both for banking or for getting access to cars or to buildings. Electronic ID cards, passports, web servers. Skype is mentioned here. Bitcoin is protected by public key cryptography, and if you really want to go down that road, so the Internet of Things, everything that is put now on the Internet hopefully uses some form of public key cryptography. And if you count up these numbers, well, you end up definitely in the billions. So these things are just used all over the place all the time. So it's a very, very important basic primitive of cryptographic digital world. Problems with it is it's actually quite expensive to sign a big message, and I'm going to tell you in a second how to do it better. The other problem is also that the systems currently used are actually insecure against quantum attackers. So they are based on factoring, based on discrete logarithms, and we know Shor's algorithm actually kills them. So in fact we are currently looking for alternatives, but the problem with those are they're even more expensive. So it makes it even harder to sign stuff, and harder, I mean, expensive in terms of time and in terms of size. And here's already a trick that helps a lot when doing this. This is the so-called hash and sign paradigm. So instead of signing immediately this huge message, so for which you need some heavy mathematics to do, what you do instead is you first hash this message down to something reasonably small, say 256 bits, and then you sign those instead. So you only have to do your heavy operation on kind of the small message here. And there's this theorem, so if H is a random oracle, then this is actually secure. So this works. So you see, random oracle model, one can actually prove that this principle works, and it's very relevant and used in practice. So I have a quick proof here, but I'm not going to go in much details. But it's very similar to before. Well, I cannot give you the details because I didn't formally define what security of signatures means, but in principle the idea is again to make a list of Eve's queries to this random oracle, and either she finds a collision, which we just saw is very hard in a random oracle, or then basically the security of the signature scheme kicks in and basically does the job. So that's a very high level intuitive idea why this works. So the last thing I want to explain you about classical crypto is how we actually build these hash functions. Now, a hash function we saw is something that takes arbitrary sized inputs and it produces a fixed size output. So how do we do this? We're not very good at designing these big things, but we are good, well I'm not, but some people in here are, designing stuff like that, so like a small building block, compression function, so-called, that say in this case maps 2 n bits to n bits, so it takes 2 n-bit strings as inputs from both sides and outputs n bits. And this construction here is known as the Merkle-Damgard Construction, where you just chop up the message that you want to hash into blocks, and maybe you do some padding, and then basically apply this building block enough times, you do some finalization, and you get the hash of the message. And again, this has very nice properties one can prove. For instance, collision resistance. So one can prove that if F is collision resistant, so if this building block is collision resistant, then so is the overall construction. It's actually not so difficult to prove. If you're bored later today, you can try that on paper. It's an exercise for students who take the crypto class. But you can do more. So where I want to go here is that you can actually prove more properties of hash function of this particular construction. Namely, you can also show indistinguishability. So what is that? Well, if F is a random oracle, so again, if these little building blocks are kind of perfect, then the overall function H, the input-output behavior is random. And what I mean, I can explain in pictures. So we kind of usually have this real world and the ideal world, and we want to compare the two. So in the real world, we have a distinguisher that interacts with this construction. So there is this Merkle-Damgard hash function. And what we want is that distinguisher shouldn't see a difference whether he's playing the game here or he's playing the game here. So whether he's actually interacting with this construction or with a real random oracle. So this is what we call indistinguishability. And in fact here it's also not so hard to prove, so once you understand this you can actually also do that. But you want to take it yet another step further, and this is the last classical thing I ask you to follow. So we want indifferentiability, so that's another thing, but it's just an extension of what I said before, so maybe I show the pictures first. So this is what we had before, that's what you just saw. Now we're going to upgrade this with yet another part. So we want to give access not only to this construction, but in fact we want the distinguisher also to be able to interact with this little building block itself. No, because this building block, again, often it's just something that is specified on Wikipedia, so why not? This guy could also interact with that. And we want that even then, it's possible to kind of simulate that behavior in the ideal world, so where you have a real oracle, and you have to build a simulator. So indifferentiability asks for the existence of a simulator, so that no efficient adversary can distinguish between these two things. And the difficult part is to kind of build the simulator. So I realize this is quite a bit to kind of take in, but somehow you see clearly it's an extension of what we had before. You kind of demand more, and you have to work quite a bit to actually make the simulator work. And you can imagine that in order to do so, you kind of need to keep lists. You kind of need to keep track what the distinguisher has already asked to this simulator, and how this could possibly be related with the real random oracle, because here clearly you see this yellow stuff also occurs here. So somehow you have to make sure these things are consistent. And for that you kind of need to, again, write down what the queries the distinguisher did, and hopefully set up your responses in a way that makes sense. So this is what we call indifferentiability. And one can actually prove this, for instance, for this Merkle-Damgard construction has been done before, like 10 years ago. All right, so far so good, still awake? It's good. It's nice to be the first speaker. I see all. Do you want to ask a question? I guess so. I don't know. I don't know who's chairing. Last time they made me chair the rest of the day. I remember. Oh, you're chairing? Okay. Okay.
For now, let's allow. No, okay. I just understand. The simulator, is it being constructed out of calls to the oracle?
Yeah, so you need to, it's not so hard to see that in fact this simulator also needs to call the real oracle in order to make it consistent. Yeah, yeah. So he can ask questions to the real oracle. It would be nice, so I think it should be efficient, ideally, yeah. Yeah. So if this guy is efficient, then everything should be efficient, yeah. All right, so now we'll... Deterministic? No, random oracle is as random as it gets. Yeah. It's consistent. If you ask the same thing twice, it will give you the same answer. Yes, it's really just a function. It's fixed but chosen at random. Yes. All right, so now we'll turn on the quantum and see what happens. So we introduced the quantum random oracle model, and basically that's what we did 8 years ago with a bunch of people, where we realized that, well, if you do post-quantum cryptography or quantum-safe cryptography, we're probably going to hear more about this, then we study quantum attackers, so attackers that have quantum computers, but they work with classical crypto schemes. So a guy like this, that he's just playing in a crypto protocol and he knows H. So if he knows H, then he can clearly look up this description on Wikipedia and run this function H in superposition on her quantum computer. So that means that in our model, we also have to allow quantum queries to this random oracle. So we need to allow the adversary. Before he was just asking classical questions. Now we need to allow this adversary to ask quantum superposition questions to this random oracle. So far, okay. So what does it mean? Let me make it a little bit more concrete, and now I'm going to use some quantum slang. Hopefully, I think most of the people have seen cats and bras before. So the standard way of modeling this is in a so-called standard oracle. It does the following. The adversary has two registers, x and y, and if you want to evaluate a function f, then the standard way of doing this is just to basically XOR the evaluation of f on x to the y register. That's how you kind of usually unitarily model the evaluation of a classical function. So, for instance, so a concrete example is the following. A quantum attacker could just evaluate this function on a superposition over all inputs. So the inputs are n-bit strings, and what you could do is create a superposition over all of them, set the second register y to 0, and then just ask the standard oracle for the answer, and she would get a superposition of all possible inputs together with the evaluation of f on these inputs in a second register. So in these branches of f's, she collects all f of x's at the same time with a single quantum query. Okay, that's something you could do. And now let me just quickly kind of change the point of view and introduce the phase oracle. So probably the experts, I know some experts here have seen this before. So this is the standard oracle. The phase oracle is defined in the following way. So you have, again, two registers x, and I call this eta now to indicate that I kind of switched some bases. And there a query to that oracle does the following. It just puts a relative phase, so -1 to the eta times f of x. So these are n-bit strings. You take the bitwise inner product, and it leaves the x and eta on its own. And I want to show you this following lemma. So there's now a little bit of math that, in fact, these oracles are equivalent. They're doing the same thing. So the standard oracle is equal to basically the phase oracle where you conjugate it with the Hadamard transform on the y register. So that's just a little bit of calculation, and let me guide you through this once. So, and it's not the full proof, but let's say we want to run this on x0. So if you run the standard oracle on x0, what you expect is this. You get x and f of x. Now if you set y to 0, that's exactly what the standard oracle should do. Now let me do the complicated way, so this way here, and explain you why we get that. So we first do a Hadamard transform on y, so that turns this 0 here into the superposition of all n-bit strings, eta. So that's just what happens if you do Hadamard on that register. Now you call, so this was that part. Then you do the phase oracle. So you call the phase oracle that puts this -1 to the something here in front. And you have to do another Hadamard, that's this one. And you end up with another sum, now say over y, and that you end up with another factor -1 here. And then it's just algebraic reformulation. You kind of put these two -1s together and you sum in the exponent, modulo 2. And then you have to realize that if you do this sum here, this blue sum, then in fact it's 0 most of the time. Because if y is different from f of x, then this is a non-zero bit string. And if you sum eta over eta and you have eta in the product with something that is non-zero, well then you have as many -1s as +1s. So this sum will be 0. And so this thing is 0 whenever they are different, and it's 1, well I'm actually omitting the normalizations here, so it's more than 1, but there's also a 1 over 2 to the n somewhere. So that's just for clarity of presentation. So this is not really 1, but it will turn out to be 1 if you normalize, if these two are equal. Well, and then both these summations are gone and you just end up with what I claimed. So that's kind of the calculation you have to do just to accept that basically the phase oracle is the same as the standard oracle, just seen from a different point of view. All right. Now, what's the trouble with the QROM? I just told you before, in the quantum random oracle model, we allow the superposition access. So what does it mean? Well, it means basically that many classical random oracle proofs break down in the QROM because you can play a lot of tricks in this ROM. For instance, I mean some things that I explained here. For instance, you can have efficient simulation. So you, as a reduction, as somebody who's playing with the adversary, you kind of want to simulate a real random oracle towards an adversary. Well, we're going to see actually in a second how to do this, but this is not so clear that you can anymore. And you can play even kind of heavier tricks. Namely, you can plant some challenge that you get on your own, if you play with this adversary, as an answer in this random oracle. If the distribution is fine, maybe the adversary will just keep playing along. You also learn what the adversary is interested in. No? If you kind of see what his queries are, well, then you can do stuff with that. But if it's a quantum query, it's not so clear anymore how to actually do that. So it's just the proofs basically don't go through anymore. And so a lot of these things need to be revisited. And these are the things that we listed back 8 years ago when we introduced this model. And I'm happy to tell you that most of these things actually we know how to solve nowadays. So over this last period we have developed a set of very nice tools and tricks to actually kind of cope with these cases. And I want to show you like the last strike to that, which is like a brilliant idea that this guy Mark Zhandry had. And it's a very simple idea that many people, or at least one, but several people in the room had already many times. In order to prove the security of quantum key distribution, what do? You look at the purified version of the protocol. You can look at the purified version. So the idea is really to purify. So here you have a random function that is kind of given to you from the outside world. Well, that's a classical thing. So if you kind of think quantum, then the natural thing is to just purify that. Introduce a quantum register that holds the description of that function. And that's exactly what Mark proposes to do. So in the standard oracle it would look like this. Before we had just x and y mapped to x and y, x or f of x. Now what you do is you just add a superposition over all possible f's to that picture. If it's a random oracle, then this database is simply a superposition over all possible truth tables. Remember, that's a huge thing. It's an exponentially large object. But nevertheless, if you just use it as a proof tool, you could introduce that thing. You can also do this in the phase oracle picture. It's exactly the same. Before we had the phase oracle, now we just add a f here at the end. And notice that from an adversary point of view, who does the queries, there's no difference whatsoever. This is really just a proof trick that you introduce, but you don't change the actual viewpoint of the adversary. Because if you forgot about that register, if you kind of traced it out, it would be like measuring it and thereby collapsing it back to a classical function, which he was... Yeah, Eve's adversary, so it's just a guy who kind of does the oracle, no? So you don't need to distinguish too many things. So Eve is just the one who plays with the oracle. All right. So now comes the cool part about this trick. Namely, it's just yet another change of viewpoint. So here this was the phase oracle we had before. Now we're going to look at the Fourier oracle. And the Fourier oracle is the phase oracle where we now apply a Hadamard transform not on the Y register but on the F register. On that thing that we just introduced, this purification register, we now look at the same thing but from a different basis. Why not? Before it was a superposition of over all function. If you apply a Hadamard, a lot of Hadamards to it, then you just end up with the all zero string. So in the Fourier domain, this database is just initialized at the 0. So you basically have this kind of truth table. So I want to show you what happens if you make a query to this Fourier oracle. So you start off with x and eta, and you just have 2 to the n many 0-bit strings in that database. Now if you do a Hadamard on that register, well, you end up with a superposition over all possible functions. Okay? Now we call the phase oracle, the way it is defined up here, so that introduces that relative phase here. And you have to do another Fourier transform on that part, so you end up with another summation. And very similarly to what I showed before, you can do a few computations, it's really not hard. And you will end up with this. So you will end up with x and eta. And now it's not just all zeros anymore, but you actually at the position x, indicated by x, so that's an n-bit string, you have 2 to the n positions, you will find entry eta here. And that's really cool, because what that actually means is that the Eve, or whoever did the query, just entangled herself with this truth table in a somehow very clean way. No, it's like when she's asking the query x eta, simply this eta shows up at the x position. So that's kind of my formal magic. I mean, so far not much has happened. But if you do that and you continue to do that, then you basically just do what was promised, namely to record the quantum queries that an attacker does. So you can do this multiple times. So if you do multiple of these FO queries, then you kind of just populate this database. There are going to be more entries that are non-zero. You have to be careful. If you query the same thing twice, then there's kind of some XORing going on, and also things are a little bit more complicated than what I explain here. But the idea is really, well, this thing kind of keeps track, so this purification register that we introduced keeps track of what the adversary actually asked. Then it's a short step to actually realize that you don't have to keep track of all these zeros here. You can simply compress that thing. So you cannot just start off with an empty database. If you do a Fourier oracle query, then you basically have to add an entry, namely at position x you have to add an eta. And then you have to keep doing that. But that means that actually this object is going to be small again. It's only going to grow with one entry, or I mean with 2 entries every time the adversary does a query. So if you only do polynomially many query, you only have to keep track of polynomial size thing here. So it's not this huge exponential stuff that we had before. And indeed, actually, if you do the math and work stuff out, then this actually allows for an efficient simulation of the random oracle to the adversary. So that's kind of the magic that has happened last year. Unfortunately, it was written in a rather inaccessible way. But nevertheless, it has already led to quite a few results. So I think here's an overview. So in that paper, Mark Zhandry himself kind of proved some form of indifferentiability for the Merkle-Damgard construction and some other results. This is an important transformation in cryptography in the random oracle model that was not known to hold against quantum attackers, and now it does. Then you can, using this technique, show some simple query lower bounds. So I'm going to I have one more slide about that. For searching and finding collisions in random functions. And then we generalize these results to actually do some more advanced, what we call quantum lazy sampling. And I'm also going to talk quickly about that. Then just last week, new papers appeared on the archive. So this is really, really brand new. Again, by Zhandry and his student, who uses this technique to analyze the Fiat-Shamir transform. That's another important ingredient in classical crypto. And other people from Japan actually solved a question that I also wanted to solve for a long time. Unfortunately, they were first. But again, using the same technique. So this is definitely not the end. So this will go on and on. I think many more applications of this will show up in the very near future. So let me to finish up, kind of quickly talk about these two results. So here are quantum query lower bounds. Somehow the intuition is an adversary, kind of as his queries are recorded in the database, he can only learn about the random oracle what is recorded there. So somehow whenever he does a quantum query, this is put in this database register, and all the other stuff, because it's a random oracle, he doesn't know. So one can prove a theorem saying that if for any quantum player making at most Q queries, exactly Q queries, if the database is measured after these Q queries, then the probability that it contains a certain pair, for instance x0, so that would mean that the oracle f of x maps to 0, so you found this x would be a pre-image of 0, the chance that you find such an entry is at most big O of q squared over 2 to the n. So again, if q is a polynomial, then this is exponentially small. So this shows that even if you have quantum access to a random oracle, it will be difficult for you, and it will take you, the success probability is low if you don't make enough queries, to find a pre-image of 0. And the proof is kind of not very new, it's just it can be now made much more compact. Basically you track the norm of the quantum state that the adversary holds projected onto the database that contains a 0. At the beginning the database is empty, so this norm is 0, and then every query can increase it by at most 1 over 2 to the n over 2. And after q queries you have q over 2 to the n over 2, and if you want probabilities, then you have to square that and you get this. So this is again like a very quick high level overview, but somehow this can be made formal and it can give you kind of an easy proof why it's difficult even quantumly to find, say, pre-images of 0. Then finally I'd like to talk about this quantum lazy sampling that I already quickly touched upon. So classically what lazy sampling is like you're lazy, so whenever the adversary asks for a new value from the random oracle, you just sample a fresh one if it's something that he hasn't asked before, and if it is, then otherwise you just give him the same value as you did before. So as long as this guy does only polynomially many query, then this is easy to do. You can also efficiently simulate that. But we saw if this is quantum, then in a single quantum query you can already kind of get information about all the function values of x. So what do you do now? Like how can you like kind of play a random oracle towards such an adversary? Well, what we originally suggested back in 2011 is, well, use a quantum secure pseudo-random function, so that's kind of the standard crypto answers. But at that point we actually didn't know if these things exist. So this only a year later Mark was able to prove that these things actually exist. And he made an even better observation, namely that if you just want a uniform function, then it's actually enough to just use 2Q universal functions. So for those who know what these are, there's kind of an efficient construction of that, and as long as the attacker does not more than Q queries, then this will look like random to him. So there's a consequence of the polynomial method for those who care. However, so we took this and we now can do better. So together with Jan, I think I saw him somewhere. Yes, there, Jan, my PhD student, and Chris Mines, who's not here, and Sebastian Zur, a master's student, we kind of generalized these quantum recording results. So now we can also handle non-uniform functions. Now before it was always for random oracles that are really uniform over all functions. But for instance, we can handle permutations, and we can somehow even kind of handle functions that are sampled on the fly. So we have more general function distributions possible. And we combine this with yet another trick that the experts know, a very recent one. And if we do that, then we end up with a kind of a game-playing framework. It's another crypto thing that people like, that are used often in classical cryptography. And we are able to show the indifferentiability of the so-called sponge construction. So this is not Merkle-Damgard, it's kind of another form of building a hash function. And what we need to prove is basically we have to prove indifferentiability. So you have to cook up such a simulator that works. But now you can imagine it's quite a bit harder, because now this distinguisher is allowed quantum queries, both to this little thing and to the big thing. And now we have to cope with that. And so basically these lists are a problem. No? Before we were just like looking at the queries that the adversary did, and now we didn't know how to do that. except we have the techniques now with these kind of recording quantum carries to actually create such lists, so they're all kept in superposition in the purification of this oracle, and therefore basically allow the classical proofs to still go through. So that's it. Maybe a quick summary. I've told you about the classical random oracle model, what it is and what people use it for. Then we saw that you get into trouble if you allow quantum access, which you should. It's a very natural model to consider that. Then I introduced this recent tool of this, say, Fourier oracle that you can actually kind of record what a quantum adversary queries in a database, and you can even compress that. And finally, we saw some recent results that uses this technique to reprove, basically re-establish the security of classical crypto schemes in this quantum random oracle model. So thanks a lot for your attention, and I'm happy to answer questions now. So maybe if you're interested in the classical random oracle model, then I can recommend this blog post by Matthew Green on this, and this is written in a very accessible way. And also my quiz actually contains some more questions where you can check whether you understood what I just said, and there's also a little evaluation part that you can fill in there if you want. So, shoot.
Some questions. Go ahead. So you talk about the standard oracle and the phase oracle. When you're thinking about quantum interactions with your oracle, are those the only kinds of protocols that need to be considered, or could there potentially be others?
Well, so in principle, all these oracles are the same. So they're all equivalent because they're just conjugation with unitaries. So in principle, nothing else happens. Then if you understand one, then you also understand how the others work. And the whole goal is just to basically evaluate the function on an input, but in a unitary way. So
basically any way of evaluating a function on an input in a quantum way can be reduced.
I would say so, but maybe you can cook up somewhere where you can't. But these are kind of the standard ways of modeling that.
Go ahead.
You say that with this recording register, it shrinks, or it can be shrunk.
Yeah.
So the idea is that somewhere in, like if you had this really big recording register, somewhere in this register it's going to put down some information that corresponds to what the adversary measured.
Yes.
But if you don't know where that information is going to show up, how do you make this register small enough?
Right. So it's not where the adversary measured. So there are no measurement here whatsoever. It's really a quantum query that's again a unitary operation. So you never, in principle, you don't collapse. You cannot. So such an oracle doesn't force the adversary to collapse its state. So there's no measurements involved. And the query is simply defined on input states, say x and eta. And what it does, and this Fourier oracle does, is just it puts at position x the number eta. And that's all that happens. And it can happen in superposition. So you can ask a superposition query, you can put x and eta on superposition, but that will just happen on every branch of the superposition.
But it seems to me that you would need all of the registers available in order for that to be possible. Maybe I don't understand.
Well, I mean, you have to be careful. So what we want to do is we want to compress this thing. So the uncompressed thing, then you substitute thing and it appears somewhere. But you're right that in a different branch of the superposition, this entry might appear at a different place. So what you need to do is you have to come up with a unitary way of compressing this down to a small thing. But of course you can. So I mean, you can just write a classical program that does this. Basically, you only kind of keeps track of certain entries. You kind of have to cook up a data structure that does that. But if you can define it on all the basis states, well, then you can also do that. I mean, in superposition.
Okay, one quick. Maybe I give the first Renato.
So this idea that an adversary can query cryptographic systems in superposition must be a problem also beyond oracles. Isn't there kind of a general way to avoid that by some maybe tricks that cryptographers could invent. For example, I mean, one could think of something like that these devices have some internal randomness that is not accessible to the outside, and whenever they get a query, they just also alter this randomness, and this then creates some entanglement cryptography. I'm just, as a thing one could imagine, are such things considered in this field, or is this?
Maybe I don't think it's like a very well explored corner. So indeed, it's a concern that has been raised, and actually I have several works in this area where you assume not only oracles where it's kind of clear that you can run a hash function superposition, but also say an encryption oracle in superposition. And you can always argue that, well, let's stay on the more paranoid side. So if you make a scheme which is also secure if you run in superposition, well then great, you will be safe against these attacks. But how can you guarantee that? I mean, I think that would be a question that I would rather ask to you. Can you actually, or maybe to Nicola, can you actually build a device of which you're sure that it cannot be put in superposition? This seems something that a physicist should be able to answer. That would be very valuable for crypto, I think. If you kind of really are guaranteed that there is some measurement or there's something you cannot access, then then this would be good. I think it would be very useful.
Let's finish with one question of Peter.
Yes, you didn't specify what you mean by security of a signature scheme.
That's right.
Within this quantum model.
That's right.
If you allow Eve to pose a question in superposition, what she may get is in superposition.
That's right.
Something where part is a faked signature on a message.
Yes.
But you have not thought how she then should extract
Yes.
the forgery from the
Yes.
cards she has produced.
Yes, you're very right. So I mean, there is a clear definition what we mean by the security of a signature scheme, so-called existential unforgeability under chosen message attacks. So an attacker is allowed to choose messages, get those signed, and then he should come up with a new forgery. So a message he hasn't asked before, but where the verification checks out. And then indeed there are two possible models. One that also Renato just suggested is like, can you run the signature oracle also in superposition or not? And so these are two different settings, and you need to build different schemes for that. But these things are defined. I didn't define it in my talk, but I'm happy to explain you in detail how this is done.
Thanks. So, thank you, Chris, for a fantastic talk.
Thank you.